two departments here. Fantastic department here of naval architecture and ocean and marine engineering, and I'm from a different department. And if there's one thing that I remember from as a child, was the concept. It took, so if I knew something about electricity, is that they always say is that never mix water and electricity. That's the one thing that I remember. And in a way, in this university, we've kind of neatly taken that to heart in lots of what we do, the way that we organise the Faculty of Engineering. Wet things are naval architecture, Naomi. Electricity is somewhere down the hill, somewhere else. But actually, when we look at offshore renewable energy, of course, the two things do have to mix. And increasingly, the bits of research that I'm involved in are very literally having water inside of electrical machines when we're generating different types of offshore renewable energy. And there are lots of different ways that we as two different departments can collaborate. So during the very short talk, hopefully I say short talk, I'm going to cover a few different points, and hopefully that will lead into some discussions over coffee. Is it just coffee, or is it coffee and cake?
Coffee and cake, or whatever.
Coffee and cake as well. Okay, that's good. So what do I work on? Briefly, my own personal research area. Who am I? That's a big question to ask and answer. A little overview of some of the offshore renewable energy, mostly wind energy research that's done down the hill in the Royal College building and over in Tick and out in Cumbernauld. And maybe some of the opportunities for collaboration. Sometimes the navigation, the geographical navigation around organisations such as universities can be quite challenging, as the earlier you are in your academic career, it's more difficult to understand how to connect to other people in different departments. So hopefully I can help with some of that. Okay, so what do I work on? So the bit that I work on is normally hidden away. Okay, which is a great shame because it's really interesting. But the bit that I work on is the wind turbine powertrain. Okay, so the bit that's inside the box on top of the wind turbine that you never get to see. Okay, the bit that connects from the mechanical power, the torque, the rotational speed from the wind turbine rotors, and then converting that into electrical power. So if we looked inside that, what's actually going on, we are doing a number of different energy conversion processes, all for very good reason. As we go through this, we often have a torque speed converter, a gearbox, where we step up speed and we reduce the torque. We have an electrical machine, which is mainly where my research background is, where we convert mechanical power into electrical power. That would take that torque and we take that rotational speed and turn it into volts and current, the stuff that will electrocute you. We often put that through a power conversion process. That's a key area that is sometimes, as engineers working offshore renewable energy, we have no sight of, but is increasingly vital to the way that we operate wind turbines. We make them work efficiently and we connect them to the grid. And then even in the grid nowadays, we have power conversion, for example, in high voltage DC power conversion. And often in that energy process, we're also transforming the voltage, increasing the voltage so that we can transmit it, or if it's in a wind farm, distribute it through that wind farm. So this is the kind of area that I'm really interested in. That's the stuff that gets me excited. And we can look at that schematically as that. And what we might see there is there are lots of different processes that are involved in there. And if we looked outside into the industry and the developing types of technologies and innovations, what we'd look at and see is actually there's a lot of differences in the way that we can do these individual steps. There's a fantastic variety. If you look at the top 10 wind turbines that are out there, there's a tremendous variety about how they do these different steps. So, for example, if I look at these two different wind turbines here, if I asked you to draw a wind turbine, you would draw 3 blades. you put it on top of a tower. Some of you that were maybe a bit more innovative might try and come up with something else, a vertical axis wind turbine or a kite or something like that. But almost all modern wind turbines look very similar from the outside. But inside, underneath, there's this great diversity of technology. It's very interesting. And these two companies here, one is Enercon, which is a German company. On the right-hand side is Vestas, which is a Danish company. Same size of wind turbine, same rating of turbine, but very different nacelle, that size of the box. And the reason of that is that they have two very different approaches to the way that they've designed their powertrain architecture. The one on this side is one that has no gearbox, no torque speed converter, and therefore the generator that's involved in that is very large. Okay, and that's why you have that kind of raindrop tear-shaped nacelle to fit that very large generator. Whereas on the right-hand side we have a gearbox, and that allows you to use a more conventional, smaller, more compact generator in there. If we were to look at what the ideal characteristics of this process, the kind of things that we would really like, if we could imagine our ideal powertrain, we would probably be looking at things which are impossible to achieve. But let us just imagine for a while designing an ideal powertrain. What would an ideal powertrain look like? Any suggestions? What features would it have?
Zero resistance.
Why zero resistance? Why? Why do we want zero resistance?
To gain more power.
To be 100% efficient. If we're going to be idealistic, then let us imagine the totally idealistic. Okay, we would like something which is 100% efficient. Okay, not possible, but let's imagine that. What else? What else would we like?
Simple.
Simple. Why do we want it to be simple?
Less maintenance.
Okay, so something that never needs to be maintained, or if it has to be maintained, it was very simple to do, very, very quick. Okay, we'd like something to never break down. We'd like it to be 100% robust and reliable. And these are all there are many other things we could go through, but these are all the different types of features which are often contradictory when we're designing something. Okay, we'd like it to be very cheap or cost nothing at all. Okay, so the designer of the powertrain is always trying to work and trade off reliability, efficiency, costs, mass, size, all these different things. And that's one of the interesting things. So these are some of the ideal things that we've talked about there. These are the very good features. So these different wind turbine designers are coming up with different powertrains and trying to find something that will eventually turn into a very low cost of energy for an offshore wind turbine. And some of them will put emphasis on efficiency, some on costs, some on capital costs, some on operations and maintenance costs, and so on and so forth. And I think that's why I find this a particularly interesting area to work on. There's this tremendous variety of technology, and also different groups of designers that are coming into quite radically different design solutions, and they're all competing against each other. Okay, so that's the area that I work in. I've not really said who I am, apart from I work in that area. So I did my undergraduate degree in a place called Durham, which is in the north of England. I trained I did a general engineering degree, so I was in a very broad engineering school. I did a PhD over in Edinburgh in 2004, 2008, and again it was in a school of engineering, which is very different to the way that we have it set up here at Strathclyde. I joined Strathclyde in 2012, and I work within the Centre for Doctoral Training in Wind and Marine Energy Systems, and I'll say a little bit about that later on. I've done a few other bits and pieces, worked out in industry, and have actually been involved in real design projects. The bits that I did for my PhD, I will try and show why this is an interesting area in terms of a picture. Okay, so my PhD was in electrical engineering, but on a kind of mechanical engineering aspect of that. And as we know, as wind turbines get bigger and bigger, the blades get bigger, and actually one of the limiting factors for a wind turbine is the tip speed. Onshore, the tip speed is about 75 meters per second, maybe 80 meters per second. Offshore, where we don't need to worry too much about noise, although we have to be mindful of some of the things that Maurizio was talking about, that tip speed might go up a little bit to 95, maybe even 100 meters per second. As our wind turbines get bigger, and offshore they are getting much bigger, we're looking at 12 megawatt wind turbines now. Our blades get longer. What does that mean? For me as a powertrain designer, it means that the rotational speed is reducing. Okay, so if we look at the next generation of wind turbines, which are 12 megawatts, they are rotating at 6 rotations per minute. Okay, that's very slow, right? There's one wave energy device that I looked at in a study. It was 1 RPM, which if you want to have a look at a clock and understand what 1 revolution per minute looks like, the clock gives it for you. Okay, so something's very slow. Electrical machines, how we generate stuff in power stations, conventional power stations, very high speed generation, thousands of RPM. So when we look at wind turbines and other offshore renewable energy systems, and we think the electrical stuff, no problem, stop for a second and think this is radically different input to the system to what we're used to. As I say, many of these turbines have a gearbox or a torque speed converter. But many of the wind turbines which are being put offshore now are moving towards what we call direct drive. So that's where we directly couple the electrical machine, the generator, to the wind turbine blades. So this 6 RPM of our blades, our rotor, means that we've got a 6 RPM of our generator. The torque rating of that generator, the size of the generator, the proportional to the torque rating, is massive, is enormous, is eye-wateringly big compared to conventional electrical generators. So these machines tend to be very, very large. And this is an Enercon wind turbine here. And I don't know if you can see the little picture of the people down here. These 3 people down here. Okay. This is an electrical machine within that wind turbine. Okay, this is 12 meters in diameter. Absolutely huge mechanical and structural device. The electromagnetic aspects of this are trivial compared to the mechanical engineering, the dynamics, the structural engineering that goes into this. And that for me is a very interesting bit of area that we look at. So I've been involved in this in different aspects, designing cleverer, smarter types of generators, ways to reduce forces or mitigate the forces in these generators. I've been involved in industrial projects, for example, for working for wind turbine companies that are designing their own permanent magnet generators. There's an example there. I've even been, before I was here at Strathclyde, involved in a remarkably unsuccessful spin-out company. So if you're ever interested in spending lots of money that belongs to other people, and you want to have some advice as to how to badly spend that money, and how to take a business plan and turn it into something that wasn't at all successful, come and speak to me, and I can give you some really good advice and a blueprint for it. However, I did, while spending those millions of pounds of venture capitalist money, I did learn a lot of interesting things. So we built some really exciting, very large electrical machines about 7 meters in diameter. So some of the research that I do now is informed by some of that, and it's also been informed by many of the great PhD students that I've had since I joined here at Strathclyde. So some of the areas that I look at are optimisation of generator and generator structures, different types of electrical machines that might be better suited to offshore energy, different types of control of electrical machines and powertrains that might have interesting features, for example, vertical axis wind turbines where there's a big torque ripple, and so that as a control problem for a generator is very interesting. And also increasingly looking at what I call parallel powertrains, so powertrains that have redundant features within them, so that if there is a failure, they can continue to work. Some of my colleagues and researchers are here, so I'm just going to borrow some of their pictures from here. But we've got a group who are looking at different powertrain research in EEE, some of whom are looking at the condition monitoring, the reliability engineering, taking some of the failure rate data and real vibration and SCADA data, introducing machine learning techniques in there and understanding how we can predict failures. So Sophia and James, who are at the back there, are leading that work. We have some colleagues who work on not just condition monitoring systems, but the idea of how to make those condition monitoring systems more robust. So a colleague there, David Ferguson, is working on that. We're doing a lot of work in terms of failure rate analysis, and we've been quite lucky with some of the work that James Carroll has been working on, where we've worked with Vestas and MHI Vestas a lot. James, who's at the back there, used to work with Vestas, so he's got lots of the access to lots of their data, their failure rate data, what the consequence of failures, the downtime and the costs. So it's something that can be really useful for analysing and understanding. I'll give you an example of that here. Along the x-axis here, we have lots of different subcomponents, subsystems. We've got them broken down into different categorization of how severe those failures are, and rank them by the number of failures per turbines per year. This is over a large number of wind farms. And one of the motivations for a lot of the research that we're doing now is that of those kind of top 10, those which are in the gearbox, those which are in the generator, those which are in the power converter, the electrical subsystems, are the ones that make massive failure rates today in the offshore sector. So that's one of the big motivations. Some of the work that Sophia is doing is marrying up the failure logs there of what's happened, along with the SCADA and the vibration data at periods before those failures actually happened. So, for example, I have a little picture here. We've got basically in the order domain, so essentially the frequency domain at a fixed speed, if you want to think of it that way, vibration measurement at a particular point in a gearbox, and the time before failure. So tracking to get closer to that failure. How did that failure start to emerge? How does it show itself within vibration? So some really interesting work in there. So far, I've really just talked about some of the existing technologies and how they might improve them in some way. But I want to just pause for a second and talk about some of the other types of technology. If I was to do this conversational talk in another 10, 15 years, perhaps what different technologies may displace some of those current technologies. So I've put some promising, and I'll put with a question mark, interesting. I'm not sure these are very good, but these are some of the things that different people are starting to look at. So some companies now are looking at the concept of if something fails, rather than removing a 6-meter diameter generator, which is stuck between my turbine and my rotor, if I imagine taking that out, can I remove one section of that system? Can I remove a module? So the modularization of this system is becoming quite an interesting area. An alternative to gearboxes, so we probably all recognise what a gearbox is, the meshing of different gears in different geometry and different gear numbers, where that in the past in the offshore renewable energy sector has been a real challenge and a real vulnerability, the idea of moving towards magnetic gears. So this is where we no longer have contact, but we're able to transmit and transfer torque and convert torque and speed. So some interesting work there. There are some very interesting, wacky, crazy different designs where trying to remove some of the loads and some of the mass. Some of these generators are becoming very, very, very large. And here are just a quick internet grab of somewhat crazy types of generators. These are generators which are very poor from a magnetic point of view, poor from an electrical point of view, but mechanically quite interesting because they're able to reduce some of the loads. Other things that we might be looking at, and people in the industry are looking at, the idea that we can convert torque, low torque, a very high torque into low torque and a low speed into high speed using gearboxes or these magnetic gearboxes. We can also use hydraulics. Okay, hydraulics in other industries are very successful with high force situations. So there's some work there. That's quite interesting. Some work that's been undertaken by a company in Edinburgh called Artemis. Work very much in some of the wave technologies, bought by Mitsubishi, actually being used in some transportation sectors as well. One of the other interesting areas that you'll see different people working on is the use of superconducting electrical machines. So superconducting electrical machines, they call them high temperature superconducting machines. They're about 40 Kelvin. So it's still quite cold, I would say. I don't know if anyone's ever tried to swim at 40 Kelvin. I would call it quite low temperature, but I guess it's a relative viewpoint. The reason that they're looking at superconducting machines is as you use superconducting, you reduce your resistance and your losses. You're able to make machines far more compact. And as we start to move from where we are at the moment, 10, 12 megawatts, up into the next big 20, 40 megawatts, suddenly the amount of permanent magnets that are being used in these machines, so that's what we mean by PM permanent magnets, the sheer tonnage of permanent magnets starts to outstrip available supplies. So there's a key resource aspect there. Okay, so those are some of the interesting areas that we've looked at and are looking at. I was going to show you some slides of some of the UK-China project that I'm involved in, which is a sister project to the one Maurizio is looking at. But I can hear cake, coffee coming. So I'm going to fast forward somewhat. If you give me, if you want to know, you can come and ask me for coffee. I'm going to fast forward here. So interesting as well. These were the best slides. It was really amazing, honestly. Great. But just a few words about what offshore renewable energy research is being done in Tripoli and the kind of opportunities to collaborate. There are a few different areas that we work in. There are colleagues who I work with who are into wind forecasting. So that's an increasingly important area. Jethro Brown. We have colleagues who are doing very unusual types of wind turbine designs, multi-rotor systems. A colleague called Peter Jameson. We've seen that with Vestas. You might start to see floating multi-rotor systems being proposed. We have colleagues who are world-renowned experts in wind turbine and wind farm control. So if you have a floating offshore wind turbine, a wind turbine is a source of loads and dynamic, but also it can be controllable, so it can mitigate some of those factors as well. We work in a department which is very much into power engineering. It's one of the biggest power engineering departments in Europe. So there's real expertise in offshore electrical networks, the grid, how the grid works, grid integration with renewables. There's a set of colleagues who work in power electronics. So power electronics is great, it helps you control the turbine, it allows what we have is variable speed. It's also a major source of downtime as well. And we have other bits of aspects there that we might want to talk about. So opportunities for collaborating with EEE, not just in offshore renewables actually. If we think about it, what other groups do we have in EEE? We have a very strong signal, image and video processing group within EEE. So increasingly in the offshore environment, trying to detect damage to something. So if you wanted to find someone who's good in that domain, what sort of expertise there. We have the Rolls-Royce University Technology Centre in Power Systems. Obviously Rolls-Royce very active in the marine sector, so the marine electrical architectures is very much, as marine becomes more electric, that's one of the propulsion is very interesting. So those are some of the other groups that you might be interested in collaborating with. One final little advert, I suppose, is that one solid example of collaboration was recently announced, which is where I work in, which is a Centre for Doctoral Training. We put in an application with REMS, the group, the CDT, which is led by Fergal Brennan, who's your esteemed colleague here, to the next round of CDTs. We're very lucky we got that awarded starting from October. And if I click through this, we've had a Centre for Doctoral Training since 2009, working in wind energy. Roberts, who was here earlier on, was in one of the second or third cohorts of that group. We started to work with Edinburgh in marine energy systems back in 2014. We've now got our fifth cohort on that. And at the same time, that was when the REMS CDT with Oxford started. We've now put in an application for a combined CDT, which is quite exciting. So from October, we will have 14 PhD students per year. They're split across the 3 different universities. But at the moment, 23 of those are funded industrially across the different partners. So we've got loads of different names that you'll recognise there. One of the partners, which is Siemens Gamesa, have pledged 10 PhD studentships, and they're increasingly working with us on a kind of strategic level. So there may well be opportunities for research colleagues within naval architecture to engage with Siemens Gamesa. There's maybe a vehicle through this CDT to work on that. That's just a little mini advert so that you know what's going on. Okay, thank you. That's all that I wanted to say.